Okay, everybody. In this video, I'm going to introduce the process of writing a proper Lewis dot structure for a molecule. In the first slide, I just show all of the various steps that we're going to take to write a Lewis structure. Before we actually go into these steps, I have to introduce a few things that we haven't talked about in lecture yet. The first is this concept of calculating the number of valence electrons. Also, we have to talk about a concept of something called formal charge, and we also have to introduce this idea of electronegativity. So we're going to start with that first, those few items first. Once we sort of introduce those, then we're going to look at this step-by-step process for a variety of different molecules, some simple and then some a little bit more complicated. So if we start, the first thing that we have to introduce is this idea of electronegativity. And when we think about a covalent bond, we spoke about this in class, in our last class. The idea of a covalent bond is that two atoms share electrons. The reason for the sharing of electrons is so that the atoms can place electron density in between the two nuclei. So atoms can move toward having this ideal electron configuration. We call this the octet rule. But in doing so, they also place electrons in between the two positive nuclei. And when this happens, atoms can lower their energy and basically become more stable as a molecule than the two individual atoms themselves. And we saw the energy well and those things in our last class. So one of the things that model we spoke about doesn't tell exactly how electrons are shared. So electronegativity gives us a picture of whether electrons are shared equally or not non-equally. So electronegativity is the tendency for an atom to draw electron density toward itself in a chemical bond. So atoms with high electronegativity tend to want to bring electrons toward themselves, whereas elements that have a lower electronegativity don't want electrons as much. So if you think back to periodic trends, electronegativity should track very nicely with effective nuclear charge. As you increase effective nuclear charge, an atom will tend to want to bring electrons toward it. That's why those atoms tend to have the smallest atomic radii. They draw electrons in toward them, toward their nuclei. So electronegativity increases as you go up and to the right on the periodic table, and this mirrors effective nuclear charge. So elements like fluorine and oxygen tend to have very high electronegativity because they have very high effective nuclear charge. So if we take a quick look at the periodic table as a periodic trend, so I just throw through the periodic table up here, and in this depiction from the textbook, each element is given a number, which is the electronegativity, and the number, as you can see, it tends to go up significantly as you go to the right or up in the periodic table. So fluorine has the highest electronegativity, and then it goes down as you go to the left to boron. So there's almost a value of 2 difference between fluorine and boron just going across that row. And similarly, the same thing happens as you go down. So fluorine really wants to draw electrons toward it, whereas something like carbon, that's a little bit more neutral towards wanting to draw electrons toward it. So now let's look at 2 different possibilities. So one possibility is that we have 2 atoms in a bond, and both of those atoms have a similar electronegativity. Now, in the case of something like carbon-carbon, a carbon-carbon bond, the atoms have exactly the same electronegativity. So when the 2 atoms are identical, you can imagine that the electron draw, will completely be equal between the 2. They'll want the electrons exactly the same. So even in carbon-carbon, this would be the case, or even in fluorine-fluorine, F2. Even though both atoms have a very, very high electronegativity, it sort of cancels itself out. So in nonpolar bonds, we call this a nonpolar bond because the electron density that's between the 2 elements are fairly equally shared. So in a carbon-carbon bond, for example, the electron density between the two. So if we sort of draw this electron density as a blob around the two atoms, no particular atom wins out. So the electrons are sort of equally shared between the two. Now, tends to be the case also for elements that have similar electronegativity. So, for example, carbon-hydrogen bonds. Carbon-hydrogen bonds tend to have similar electronegativities. So even though carbon and hydrogen have slightly different electronegativity numbers, they're close enough that the electron density is equally shared. So you can draw this picture where you can kind of create this spherical blob around the two atoms, and that spherical blob denotes that electrons are sort of equally shared, that the electron cloud sort of spreads out and no one particular atom wants it. So when you have a nonpolar bond, there is no difference in the charge, in the spatial charge, meaning that electrons are sort of equally distributed around the two. Now let's look at the case of where we have different electronegativity. So if we were to draw a C-Cl bond, chloride is further to the right on the periodic table. So chloride is going to want to tend to pull electrons toward it. So if we were to draw the electron density, what kind of tends to happen here is that carbon gets a little bit of the electron density, but chlorine tends to get a lot more. So we kind of show that the electrons tend to get pulled over toward the chloride. Now the way to think about this is we go back to our basketball analogy. So in a carbon-carbon bond, you can think of two people bouncing a basketball back and forth. The carbon atoms want the basketball equally, so they sort of bounce the basketball back, and both partners share the basketball. Both partners share the basketball equally, so they have the basketball for the same amount of time. Now, in a polar bond where chloride wants the electrons a little bit more, it has a higher electronegativity, the tendency is for the chloride to hold on to those electrons. So as the carbon bounces the ball to the chloride, it's going to hold on to it for a little while longer. In reality, the way this sort of plays out is that the chloride actually draws the electron density toward it, creating a little bit more dense electron cloud on its side. So if you were to think about the charges in this case, this is going to give a slightly negative charge on the chloride side and a slightly positive charge on the carbon side. So these symbols that I wrote, these denote a space charge where the chloride has a slightly negative charge to the molecule. We can also denote this with what we call a dipole moment. So another way of sort of thinking about this is we can draw an arrow in the direction where the electrons are going to get pulled. This little arrow is indicative of what we call a dipole moment. This is the pull of electrons toward a single atom. So chloride pulls the electrons toward it. It has a dipole moment, and you get a slightly negative charge. Now, in the case of the carbon, you can imagine that there's two little dipole moments, but they're sort of pulling equal and opposite to each other. So there's no net dipole moment in this case. And the same goes for the carbon-hydrogen bond. But for something like carbon chloride or carbon oxygen, you're going to get a net dipole moment, and that's going to pull electrons toward it. So this is how we get. This is sort of the difference between a polar and a nonpolar bond. And as we get into molecules, we're going to see how this actually affects the polarity of an entire molecule. That's going to be coming down the pike. But first, we have to understand how this affects just a single covalent bond, meaning two atoms bound together. And this will also determine where we put negative charges. So with electronegativity, atoms that have greater electronegativity will tend to want to have negative charges. They can support having more electrons around them. So that's why this is important to understand electronegativity and dipole moments. Now, if you look, I kind of summarize at the bottom of this slide down here. You can have what's called the nonpolar bond. So this is a nice depiction. You get no partial space charge, and this is when you have equal electronegativities. So when you have a polar bond, you do have a partial charge. You get a slightly negative charge on this side and a slightly positive charge on that side. You have unequal electronegativities where this element where this element has a greater electronegativity. You can see it pulls the electron density toward it. Now, an ionic bond follows the same principle. So in polar and nonpolar bonds, if you kind of look at these two together, these are covalent bonds. In the case of an ionic bond, it's almost the extreme example of a polar bond. In the case of an ionic bond, electron density is no longer shared. The difference in electronegativity is so great that the non-metal actually rips the electron off of the metal, and you get a fixed charge. So in an ionic bond, there is no sharing of electrons. You get just a fixed negative charge. So you can assign that a negative charge to the anion, and you get a fixed positive charge at the cation. So ionic bonds are different from covalent, but they follow this same idea of difference in electronegativity, except it's a sort of a matter of degree. In an ionic bond, the electronegativity is significantly different, and you can actually get separation of charge to the point where you form ions. Whereas in a polar covalent bond, the electronegativities are somewhat different, but not different enough that you can actually rip the electron off of one of the atoms. So it is important that you understand the difference there. So now the other thing that we have to look at is this concept of valence electrons and formal charge. So valence electrons, we kind of have to go back to our understanding of the periodic table. We know what a valence electron is. Valence electrons are electrons from the outermost shell. So the example that we could use is carbon. If we write down the complete electron configuration for carbon, we get 1s2, 2s2, 2p2. So we know that carbon has a total of, I guess, 2, 4, 6 electrons, and these 4 outer electrons form the valence electrons. So the valence electrons are going to be in the outermost shell, which is the second shell for carbon, and we get a total of 4 valence electrons for carbon. So what's actually interesting is that we don't necessarily have to write the electron configuration out every time. If we flip back to our periodic table, we can start to think about this as more of a periodic trend than anything else. So anything in the first row, this is going to have the configuration S1. So these are going to have 1 valence electron. Anything in the second row, this is going to be this is going to be S2, so that's going to have 2. Now, generally, for the Lewis structures that we're going to write in this class, we don't deal with the D metals. You could deal with them if you wanted to, and you would follow the same trend. But we're going to just skip to the main group, P block elements, because we tend to focus on those. So really, what you're going to be concerned with is boron having 3. So this boron has a 2s2, 2p1 configuration. So s2 plus p1 is going to give 3. As we go across, we're going to get 4, then we're going to get 5, and then we're going to get 6, and then we're going to get 7, and then finally the nobles with the noble gases, which are not shown here, those are going to get 8. So when you're coming up with valence electrons, you really just need your periodic table, and you count across, sort of knowing knowing what we know from chapter 7 and 8 about electron configurations. So that's pretty easy to figure out the valence electrons, and we're going to kind of use this as we start to write the Lewis structure. So we'll practice this as we go on. Now, formal charge is something that you guys haven't seen yet, and is something that we're going to introduce now. So a formal charge is basically when we have a molecule. So let's just start to draw our first structure. If we draw carbon dioxide. So inevitably down the road, you're going to learn how to draw one of these structures, but I just drew the Lewis structure for carbon dioxide. What we see is we have a carbon that's bonded to an oxygen, to 2 oxygens, and the bonds are symmetric. We get 2 double bonds. So remember, these double lines here, these denote bonding electrons. And then we have these other lines that are here. These denote what we call lone pair electrons. So bonding electrons are electrons that are shared between two atoms. Lone pair electrons are electrons that are only on, for example, the oxygen in this case. Now, another way that you could draw this, instead of using the lines, would be to draw it with dots. Some people like the dots, and some people like the lines. Personally, you're going to see that I like the lines, where dots that are between two elements are bonding electrons. Dots that are on an element that are not in between two atoms are lone pair electrons. So lone pairs are electrons that are owned by the oxygen atom in this case, whereas bonding electrons are shared between the two atoms. So if we want to calculate formal charge, we're going to use this equation where we have formal charge is equal to the valence for V, valence. LPE stands for lone pair electrons. And then we have 1/2 the number of bonding electrons. So basically what we're saying is we need to have the lone pair and bonding electrons add up such that we get to the valence electron. So if we have a zero formal charge, meaning that the element is happy, the sum of the lone pair electrons and 1/2 of the bonding electrons will add up to that of the number of valence electrons. So it's basically just a calculation, and you have to recognize how to count each one. Now, the reason why it's 1/2 of the bonding electrons is because the bonding electrons are really shared. So the way this treats this is that the lone pair electrons are owned by the atom. It counts those fully, whereas the bonding electrons, it only really counts this as one electron of the two, because you think of the two atoms as sharing those electrons. So let's do the calculation here for carbon first. So for carbon, the formal charge is going to equal the valence electron. So carbon should have 4 valence electrons. It's 2s2, 2p2. So that's 4, but we can also just look at the periodic table and see that it's in that row, that 4th row. Now let's look at the number of lone pairs on carbon. Well, in this case, there are 0 lone pairs on carbon. So we write a 0. And now we're going to count up the number of bonding electrons. So in this case, there are 1, 2, 3, 4 bonds. So that means that we're going to have 8 bonding electrons. Each one of those bonds has 2 electrons in it. So we're going to take 1/2 of 8. This is going to give us a grand total of 0. So 4 minus 0 minus 1/2 of 8 is 4, is going to give 0. And if we do our oxygen formal charge, in this case, our oxygen should have 6. Our oxygen has 2 lone pairs, so that's 4 electrons that are in the lone pairs. And then we're going to take 1/2 of the bonding electrons, which for each one, there are 1, 2, 3, 4 bonding electrons. So we're going to take 1/2 of 4. So 6 minus 4 minus 1/2 of 4 is 2, is going to equal 0. So the formal charge calculations, when an element is happy, generally this will give you a formal charge of 0. If an element has a slightly different number of bonding and lone pair electrons than its valence electrons, then it's going to have a bit of a charge. So if it has a little extra electrons, it'll have a minus charge. If it has a few less electrons than its valence electrons, it will have a slightly positive charge. And we'll see both cases as we do some examples. So now we can go into our steps. So we're going to refer to these steps going forward. And in each case, so in essence, what we're going to do is, for our steps, we're going to calculate the number of valence electrons. We're then going to write a skeletal structure. So for the skeletal structure, we have to know about electronegativity. So we're going to pick the least electronegative atom and put it at the center. The reason for this is because if you think about it, the more electronegative atoms are going to pull electrons toward it. So it's unlikely that highly electronegative atoms are going to be in the middle. they're going to tend to want to be on the outside, and they're going to pull electron density away from the central atom. Now, one caveat to this is hydrogen is typically never at the center. And the reason in this case is because hydrogen can only have 2 valence electrons. So it's unlikely that other atoms will be able to steal enough electrons from hydrogen to form a complex structure around it. So once we have the skeletal structure, we're going to distribute electrons around the central atom. We'll look at how we do that. Then we're going to distribute the remaining electrons to the central atom. And the main thing is going to be creating multiple bonds to satisfy the octet rule. So at first, we're going to look at this for just molecules in the second row and above. But then we're going to introduce this concept called expanded octet for atoms that are in period 3 and below. And then we're going to look at how to do multiple bonds. So let's jump right in and look at a bunch of structures. So we'll start with a simple one like water, H2O. So our first step is always to come up with the number of valence electrons. So I like to do that in sort of a very systematic way. For each element, I write the element down, and then I put the number of valence electrons that are associated with it. So oxygen should have 6 valence electrons. If you count over on the periodic table, oxygen has 2s2, 2p4. So that's going to give us 6, but you could just look to see where it is in the periodic table. Now we have 2 hydrogen atoms, so I'm going to write 2H, and I'm going to figure out how much each of those brings to the party. So that's going to be 2 times 1 electron each. So if we add this up, 6 plus 2 is going to give us a grand total of 8 electrons. So we know that we're going to have a grand total of 8 electrons to play with when we write this structure. That's our total number of valence electrons from all the atoms. So then we're going to write our skeletal structure. So in this case, we just have our oxygen. Now, like we said, hydrogen is never the central atom, so we're going to put the 2 hydrogens around it, and we're going to draw a bond in between. So we have our skeletal structure here. We have a hydrogen bonded to the oxygen, and then a hydrogen bonded to the oxygen. And now we have to start accounting for our valence electrons. So over here, I'm going to write our total number of valence electrons, and then I'm going to subtract the number of bonding electrons that I put into the skeletal structure. So we're going to take away 4 electrons. There's 2 electrons in each of those bonds that we drew. So this is going to leave us with a grand total of 4 electrons, which we're going to now start to distribute. So following the steps, we can't distribute them onto the hydrogens. Those are the outer atoms. The reason for this is because hydrogen can only have 2 electrons. Its maximum electron configuration is 1s2. So hydrogen will only ever form a bond. It will never do anything more than that. You can't put any lone pairs on hydrogen because it can't have more than 2 electrons. So the only place that these 4 electrons can go is onto lone pairs on the central atom. So we go to the next step. So we're going to put 2 lone pairs on the central atom. That's going to give us a grand total of 4 electrons, which brings us down to 0. So we've essentially accounted for all of our valence electrons at this point. Now, so let's take a look at the structure. Have we satisfied the octet rule for all the atoms? Well, for the hydrogens we have. The most that hydrogens can have is 2 electrons. So by sharing electrons with the oxygen in this bond, that takes care of our hydrogen atoms. And if you count up the number of electrons around the oxygen, we get 1, 2, 3, 4, 5, 6, 7, 8. There are 2 bonds, that's 4 electrons, and then there are 2 lone pairs. So this is good to go. And now, just to practice, let's do a quick formal charge calculation on oxygen. So for a quick formal charge calculation, it's not necessary to do this, but we'll just do it real quick as practice. In this case, we have 6 valence electrons from our oxygen. We're going to subtract away the 4 lone pair electrons, and then we're going to subtract away our 1/2 of the 4 bonding electrons. So we have 2 bonds with the hydrogens. That gives us a total of 4 electrons. So in this case, this is going to give us a grand total of 0. So It makes sense because this molecule has no charge. So every atom should have a 0 formal charge. Or at least the formal charges should all add up to 0 because the molecule itself has no charge. So in this case, that makes sense. And for the hydrogens, we have a formal charge. We have a possibility for one. Oops, let me just turn this into a 1 here. So hydrogen brings 1 valence electron to the party. It has 0 lone pairs, and it has 1/2 of 2 electrons. So this is going to give us a 0. So as you can see, this structure makes perfect sense. The oxygen has its octet rule satisfied. The formal charges for all atoms are 0. We're good to go. So now let's look at an element, let's look at a molecule where we actually start to have some charge. So in the case of NO3-, the overall molecule in this case is charged. So we're going to look at how to handle that. So our nitrogen is going to bring 5 electrons to the party. Nitrogen has a 2s2, 2p3 configuration, giving us 5 electrons. We have 3 oxygen atoms. If you multiply 3 times 6, that's going to give 18 electrons. Now, we have this minus charge. So we know that this molecule has 1 extra electron added to it. So we're going to put 1 extra electron. This comes from the minus charge. So we have 5 electrons from the nitrogen, 18 electrons from the 18 electrons from the oxygens, and 1 electron that comes from the minus charge of the entire molecule. So if you add this all up, we're going to get 24 electrons. So now let's create our skeletal structure. So when making the skeletal structure, we're going to choose our least electronegative atom to go in the middle. That's going to be our nitrogen, and then we're going to draw our oxygens around it. So again, we select the nitrogen because it's the least electronegative. So we're going to take our 24 valence electrons all together. We're going to subtract away 6 electrons from the bonding, from the bonds. This is going to leave us with a grand total of 18 electrons. So now the next step is to start to distribute the electrons around the outer atoms. So we're going to start to put those in as pairs. So we're going to do 1 pair, 2 pair, 3 pairs, 4 pairs, 5 pairs, 6 pairs, 7 pairs, 8 pairs, 9 pairs. So those 9 pairs that are going in, that's going to give us our 18 electrons from the lone pairs. So now we're going to subtract away 18, that gives us 0. So now if you move to the next step, we have to satisfy the octet rule. So in this case, what we're going to do is we're going to move we have to satisfy the octet rule for the nitrogen. Oops. So we're going to actually have to move some electrons around. So if you look, the nitrogen, each of the oxygen has an octet. So each oxygen has 4 pairs around it. Any one of these oxygen is going to have 3 lone pairs, that's 6, and 1 bonding pair. But the nitrogen itself has only got 6 electrons, 3 pairs. So to satisfy the octet of the nitrogen, we're going to erase one of those lone pairs, and we're going to move it into making a double bond with the nitrogen. So in this case, what we're going to have is we're going to shift one of those lone pairs on the oxygen into the middle here, and that lone pair is going to make a double bond with the nitrogen. So now what you find is that nitrogen has 1, 2, 3, 4 bonding pairs. That's going to give us a grand total of 8 electrons around it. This oxygen that is in the double bond is going to have 8 because it has 2 bonding electrons and 2 lone pairs. Then the other oxygens are going to have a single bonding pair, but 4 lone pairs. So, but 3 lone pairs. So that gives you a grand total of 8 electrons for each element. So that's the reason why we make the double bond in this case. It just allows us to satisfy the octet of the nitrogen atom. So now let's look at formal charge for each one of these atoms. So we're going to do this stepwise. We'll do this for each one. So let's start with the nitrogen first. So we're going to come down here and we're going to do our formal charge. So the nitrogen has 5 valence electrons. It has no lone pairs, and it has a total of 8 bonding electrons. Each of these bonds, it has a total of 4 bonds. Each one has 2 electrons in it. So we have 5 minus 1/2 of 8. That's going to be 4. So this is going to give us a +1 charge. So we get a +1 formal charge on the nitrogen. Now let's look at the oxygen that's got the 3 lone pairs and the 1 bond. So if we look at this type of oxygen, we do our formal charge calculation. This is going to have 6 electrons. It's going to have 6 electrons from the lone pairs. So there are 3 lone pairs on each on the atom, and then we have minus 1/2 of 2 electrons. So the 2 electrons come from the bonding pair. So this is going to give us 6 minus 6 minus 1/2 of 2 is a -1. So we have a positive on the nitrogen. We have a -1 on the oxygen. This oxygen is the same. We're going to have a -1. And now let's do the other oxygen that's over here. So this oxygen, if we do the formal charge, this is going to be 6 minus 4 minus 1/2 of 4. And the way that I came up with that was 2 lone pairs gives 4 electrons. 2 bonding pairs gives 4 electrons, so we take a half. So this guy is going to be 6 minus 4 minus 1/2 of 4 is equal to 0. So we have 2 minus charges for these oxygens, and then we have a plus charge for the nitrogen. So overall, 2 minuses and a plus is going to give us our overall minus charge for the molecule. So we denote the charge for the molecule by placing this little bracket up at the top and then putting the charge there. That's an indication that this molecule has a total overall charge of a -1. Now this makes sense. If you add up all the formal charges, it should add up to the overall charge of the molecule. We have 2 negative formal charges and 1 positive formal charge, giving us an overall negative formal charge. So that's how you handle a little bit more complicated structure. Now, we're going to actually look at this structure in a little bit more detail when we talk about resonance. But for now, let's just write this structure and kind of get the Lewis structure down before we start thinking about drawing more than one type of Lewis structure. So now let's look at another example. We can skip here HCN. Oh no, let's do HCN actually. HCN is a good example. So we'll do the HCN next. So with HCN, we're going to have our nitrogen atom is going to bring 5 electrons. Our carbon atom is going to bring 4 electrons, and our hydrogen is going to bring 1. This is going to give us a grand total of 10 valence electrons to play with. So we're going to draw our skeletal structure. Hydrogen's never in the middle. Nitrogen has a slightly higher electronegativity since it's to the right of carbon, so that's going to not be on the central atom. But actually here I underline carbon because I wanted it to be very clear that that was going to be the central atom. So if we take our 10 minus 4, that's going to leave 6 electrons. So we're going to place those 6 electrons around the nitrogen. That's our next step. We place the remaining electrons onto the outermost elements. So the only one that can take electrons is nitrogen because hydrogen can only have 2. And now we have to make some. Double bonds. So to satisfy the octet, we have to move at least 2 of these over to make bonds with carbon in order to satisfy its octet. Because right now carbon only has 4 electrons. So to do that, we're gonna have to erase some bonds. So yeah, let me just grab my eraser here. So we're going to have to erase two of these bonds and shift them over as multiple bonds, like we say in our steps. So we took those two lone pairs and we moved them into our we moved them from lone pairs to bonds, because now carbon has 1, 2, 3, 4 bonds, and it has 8 electrons around it. So we've satisfied the octet of the carbon, and we can do formal charge. So now every single element is happy, because nitrogen has 1, 2, 3, 4 groups around it. Carbon has 1, 2, 3, 4 groups around it, and hydrogen has just one pair of electrons around it. So we've accounted for all of our valence electrons. Let's do formal charge. So for the nitrogen, in this case, our formal charge is going to be the 5 electrons minus our 2 electrons from the lone pair minus 1/2 of 6 electrons is going to be 5 minus 2 minus 3 is 0. For our carbon, formal charge is going to equal 4 minus 0 minus 1/2 of 8. There are 8 bonding electrons around it. That's going to give us a 0. And for hydrogen, formal charge is going to equal 1 minus 0 minus 1/2 of 2. That's going to give us a 0. So the fact that all of the elements have 0 formal charge and the molecule has 0 formal charge makes sense. So we're in good shape. You guys can practice the NO plus on your own. We're going to look at one other example that I think is a good one to see. So CO32 minus is an example that we're going to look at in a second. Oops, sorry guys. CO32 minus is an example that we're going to look at in a second for resonance. But the other one that I wanted to look at to show you guys is COF2. This is a really good example of how we can use formal charge to help us. So in this case, we can write our carbon's bringing 4 electrons to the party. Oxygen is bringing 6 electrons. We have 2 fluorines, so each one of these brings 7 electrons. Times 2 is going to equal 14. So this is going to give us a grand total of 24 electrons. And let's draw out our skeletal structure. So we have carbon, that's going to be our central atom. We have oxygen, and we have our 2 fluorines. So in this case, we have 6 electrons that are in bonds. So we're going to minus 6. That's going to leave us with 18. So we're going to fill in the rest with electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's our extra 18 electrons as lone pairs. And we see immediately that the carbon, we're going to have to make some kind of double bond because the carbon doesn't have an octet. So now the question is, we can go 2 different ways here. We can draw a structure that looks like this. So I'm going to draw them kind of a little bit further down, down here. So we could draw a structure that looks like this. Where we make the double bond from the oxygen, or we can draw a structure that looks like this, where we make a double bond with a fluorine. And we have to make a decision as to which one of these 2 is the better structure. So the way that you're going to make this decision as to whether or not you're going to make the double bond from the oxygen or whether you're going to make the double bond from the fluorine is to do some formal charge analysis. So we're going to start to do formal charge a little bit quicker. For carbon, we're going to see that this is going to be 4 electrons minus 1/2 of 8. That's going to give us a 0. So the 0 is actually, in both cases, going to be the same. The carbon really doesn't care where it gets the electrons from. It's going to be the outer elements that are going to determine in this case. So let's look at which structure is going to be more stable. So in this case, if we do formal charge for the oxygen, this is going to be 6 minus 4 minus 1/2 of 4 is going to equal 0. So this guy gets a 0 formal charge. And let's look at the fluorine in this case. This is going to be 7 minus 6 minus 1/2 of 2. So that's also going to be a 0. So this structure looks pretty good. This minimizes formal charge, meaning that all of the atoms have 0 formal charge. Now, if you look at this structure, this oxygen atom is going to have 6 minus 1/2 of 2. So this is going to be a -1 for that oxygen. And this fluorine is going to be 7 minus 4, 2 lone pairs, minus 1/2 of 4, 2 bonding pairs. So 7 minus 4 minus 1/2 of 4 is going to be a +1. So in this case, we actually see that we have non-zero formal charges. So we want to choose a structure that lowers the formal charge the most. When we say lowers the formal charge, we don't necessarily mean the overall formal charge, but it gives the least number of formal charges on all the atoms. So this is going to be the structure that we choose. This one has the least amount of formal charges going across. This one, on the other hand, we're going to reject because it's very unlikely that fluorine is going to want a positive charge at all, because fluorine is definitely the most electronegative atom. So on this structure. So the likelihood that a positive formal charge would be on the fluorine is very unlikely. So this kind of gives you some examples of looking at different things, how to calculate formal charge, how to create the structures. This is a great example. And you can practice with NO2 minus, NH3, and NO plus. Those are good examples. We're going to now just look at a special case called resonance. So resonance is an interesting case where you can write a structure more than one way, but get the same exact answer in terms of the way the structure looks and formal charge. So let's look at that case of CO3 2-. If we wanted to draw a Lewis structure for this one, carbon is going to bring 4 electrons. We have 3 oxygens, so this is going to be 6 times 3 is equal to 18. And then we have our charge, which is equal to 2. So that's going to bring 2 extra electrons to the party in this case. So we're going to get 24 electrons total, 18 plus 2 plus 4. And now let's draw our skeletal structure. So we're going to have carbon in the middle. It's the least electronegative atom. So we're going to have our 3 oxygens around it. And we're going to get, we're going to start to do our accounting. So we have 24. We put 6 electrons as bonding electrons. This is going to leave us with 18. So now we're going to start to put our electrons around. And that's going to get rid of the remainder of our 18 electrons. That's going to give us 0. Now we know in this case that we're going to have to do something with a multiple bond because the carbon only has 6 electrons around it. So we're going to shift one of those lone pair electrons into a double bond. This way we get 8 electrons around our carbon atom, and this is going to leave us with 2 different types of oxygen atoms. One type is going to have a double bond with 2 lone pairs, and then the other 2 are going to have single bonds with 3 lone pairs. Now, in this case, you can kind of see how it differs from the previous example, COF2. Whether we take it from this oxygen or one of the other 2 oxygens, there probably isn't going to be a preference because all of the oxygens should be basically the same. But let's just do some formal charge work to make sure that we have this all figured out properly. So if we want to do the carbon, our formal charge is going to be 4. That's our valence electrons. Minus the 4 electron, minus 0 lone pair electrons, minus 1/2 times 8 bonding electrons. So this is going to give us 0. Now we have 2 different types of oxygen atoms. So let's look at type 1. So this oxygen atom, these are the oxygen atoms that are the ones with the 3 lone pairs and the 1. So I'm going to draw my little formal charge of 0 there. So for our oxygen atoms that are written with the 3 lone pairs and the 1 bonding pair, that's going to be 6 electrons minus 6 electrons from the lone pairs minus 1/2 of 2 electrons in the bonding pair. This is going to give us a -1. So each of these oxygen atoms are going to have a -1 formal charge. Now the other oxygen atom is going to be this one. This is going to have 6 minus 4, 2 lone pairs, minus 1/2 of 4 electrons, 2 bonds, is going to give us 0. So that guy is going to get a 0. Now this all makes sense because we have our 2 negative formal charges. So we get our overall charge of -2. So now let's go down here and draw our structure out. Okay. So what's to say, just because we arbitrarily chose to put the double bond on this oxygen, what's to say we couldn't do the same thing, but instead of putting the double bond on the oxygen to the right, what if I chose to put the double bond on the oxygen on the bottom? Does this actually make a difference? So in this case, these guys are going to be the ones that get the -1 formal charge, and these ones are going to get 0. And the one at the bottom is going to get the 0 formal charge. So what's interesting about this is that this structure and this structure, you really can't distinguish between the two of them. No structure, the one on the left or the one on the right, neither one is really better than the other. They're both basically identical. The only thing that we changed was which one of the oxygen has the double bond. And we can actually draw a third structure where we move the double bond all the way over to the left. And again, we are just moving around where we're putting the formal charges. So there's nothing in any of the rules that says that any one of these particular structures is better. This concept that you can draw multiple Lewis structures without any one particular Lewis structure being preferred is the essence of what we call resonance. So resonance, if we had to give this a definition, is where you can have multiple equivalent Lewis structures. And by equivalent, what I mean is that they have the same formal charge, and there's no real preference from one to the other. There's no rule that says, nope, you can't have this structure for sure. And any one of them is actually going to be okay. So when you're drawing resonance structures, if we ask you to denote that there's resonance, this is one way of doing it. You show the 3 different resonance structures, and you use these double arrows to denote that they can go back and forth. So what actually happens in this case is you don't actually have 3 different Lewis structures. You actually just have one. So what this boils down to is really just a single Lewis structure where you have what's called a partial double bond. So you don't actually have 3 different Lewis structures where you have one double bond and 2 single bonds. What you really have is you have a single Lewis structure that has 3 pseudo double bonds. Now the reason why we know this experimentally is that in reality, one proof for one proof for resonance is bond length. So when you look at carbonate and you look at the bond lengths in carbonate, you don't see two different bond lengths, right? So the double bond and the single bond should have two different bond lengths. This should be a relatively short bond length. This should be a relatively long bond length. We'll talk a little bit more about bond length and bond order as we get into chapter 10. But for the time being, a double bond, you can imagine, brings the two atoms closer together, whereas a single bond is not as strong, so the atoms are a little bit further apart. So if we were to have this structure where we had distinct single and double bonds, the bond length should be different. But in the case of resonant atoms, the bond lengths are found to be all the same. So what this tells us is that actually these bonds are not different single and double bonds, but they're actually all sort of pseudo double bonds, where this double bond gets distributed. The other thing is related to the chemistry of these molecules. If they were to have different single and double bonds, the reactivity of those single and double bonds would be different. The chemical reactions that this would do would be different. The reactivity of the single bonded atoms would be different from the reactivity of the double bonded atoms. However, we don't see that in all of the different spectroscopic techniques and all of the different chemistry. These oxygens tend to behave similarly. So with resonance, we find that this is sort of an exception to our understanding of Lewis structures. The way to think about a resonance structure is that there are three different structures that sort of depict a double bond that moves around or is sort of spread out across all the possible places that the double bond could be. And it's important that you understand those things about resonance. We're going to talk a little bit more about resonance in class. We're going to look at a different example, but this is a good operating way of understanding resonance. So now there's one other aspect of Lewis structures that we have to think about, and this is what happens when we have something called expanded octet. So the octet rule, we've talked about the octet rule. This is basically when atoms get 8 electrons, they tend to be happy. Atoms with 8 electrons are most stable since a noble gas configuration is achieved. And this sort of works very well for our understanding of elements in the second period. These elements have configuration 2s2, 2p6. This gives us our noble gas configuration for that row. And this works really well because they have access to only s and p orbitals. So s2p6 gives 8 electrons. In the second row, L can be either 1, which is a p, or 0, which is an s, so we're kind of very happy with that configuration. But something interesting happens. When you go to row 3, elements no longer just have L is equal to 1 or L is equal to 0. In row 3 and below, n, we now have larger values for n. So n can either be 2, 1, or 0, d, p, or s. So these elements can actually break the octet rule since they can have a maximum of 18 electrons. We're not held to this idea of only having 8 electrons. These can access those empty d orbitals. Now, just because an element has d orbitals, just because an element doesn't have electrons in the d orbitals, doesn't necessarily mean that it can't access them. They're there. The d orbitals are there. We know that because n is equal to 3. Therefore, 2 is an allowed value for L. So just because they're empty, it doesn't mean that it can't access them. So with elements in row 3 and below, formal charge is used to determine the number of electrons that the central of atom should have. Not necessarily just the fact that it should have 8. So let's look at an example here of SO42-. Sulfur is in the third row. So let's sort of use the principles that we've been using to come up with the Lewis structure for SO42-. So S is going to bring 6 electrons to the party. It's actually, S is in the same row as oxygen. It's just same column as oxygen. It's just one row down. Oxygen is going to bring 6 electrons. There's 4 of them. So this is going to bring a grand total of 24 electrons. And then we have 2 minus, which gives us an extra 2 electrons from the charge. So this is going to give us a grand total of 32 electrons that we have to play with. So now let's draw the structure out as we would draw a structure for using our rules. So we're going to create our skeletal structure. We place S in the middle because S is going to be slightly less electronegative than oxygen. It's a little bit lower down on the periodic table. This is going to give us 8 electrons that we can take away, giving us 24 electrons to play with. So we start to put those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's our 24 extra electrons. We go to 0. Now let's do some formal charge calculations. So if we were to do formal charge on this guy, we will do this for the different atoms. If we were to do formal charge, let's start with the sulfur. So for the sulfur, that's 6. We have 0 lone pairs, and we have 1/2 of 8 electrons around it. That's going to give us a +2 formal charge. So we get +2 on the sulfur, and the oxygens are all the same. So in this case, we're going to get 6 minus 1, 2, 3 lone pairs. So that's going to be 6 minus 1/2 of 2. That's going to be a -1. So that's going to give us -1, -1, -1, -1. If you add this all up, we're going to get -1, 2, 3, 4 plus 2 is -2. So just using our basic rules of drawing a Lewis structure, this gives us a pretty good Lewis structure. Everything seems to make sense. We have all of our formal charges add up to our -2 charge. Everything has an octet. We're good to go. We shouldn't necessarily need to go beyond this. Well, it turns out that you do need to go beyond this. So in this case, if you were to write this structure on the exam, you would not get full credit. This is actually not a proper Lewis structure. We have expanded octet in this case. Because sulfur can access its d orbitals, we can lower those formal charges. So we can lower formal charge by creating multiple bonds. So sulfur is not limited to just having 8 electrons. Sulfur can have more than 8 electrons. So if we want to reduce sulfur's formal charge, what we can do is we can create 2 double bonds with the oxygens. And I'll show you why we do 2 double bonds. But you can actually iteratively do this. I sort of see it because I see in this case that sulfur has a +2 formal charge. So I know it needs 2 more electrons, which means that I can pull lone pairs from 2 of the oxygens to give me those 2 electrons. That's why I chose to make 2 double bonds from the oxygens. And you'll see when we do formal charge that this is going to work out to be the right case. But what's interesting here is that we see that no longer does S have only 8 electrons. In this case, it now has 1, 2, 3, 4, 5, 6, 12 electrons around it. And this is because S can have expanded octet. It can have a maximum of 18 electrons. So let's do formal charge calculations for this structure. So just so that everybody's clear, I just moved a lone pair from the oxygen into a bonding pair. So we have 6 minus 0, no lone pairs, minus 1/2 of 12 electrons. This is now going to give us a 0. And we have 2 different types of oxygens. So we have the oxygens that look like this. So these guys are going to be 6 minus 4 electrons in the lone pairs, minus 1/2 of 4 electrons. That's going to give us 0. And then we have these 2 guys. This is going to be 6 minus 6 minus 1/2 of 2. That's going to give us our -1. So now we have our -2, and as we can see, by expanding octet, we've gone from having a +2 formal charge and then 4 -1 formal charges to just simply having 2 -1 formal charges on the oxygens. And this makes a lot more sense when you think about the structure. Now, this is a great example of where we can have resonance. So we could draw many different resonance structures for this. The double bonds can move around. So a great way to draw this structure is actually to depict that resonance is to draw our partial double bonds. So in this case, we can delocalize those double bonds over all of the oxygens. So this sort of denotes our resonance, or you can draw the resonance structures like I was about to start to do. So you could draw, for example, one of the other resonance structures would be where we put the double bond down here, we put the double bond over here, we put the single bonds over there, and you could go so on and so forth. This is one way to draw the resonance. This is just another way to draw the resonance where you show that the bonds are delocalized over all the different atoms. But again, this is exactly what happens with SO42-. We see this sort of pseudo double bond distance. So not only does the spectroscopy, which is what allows us to measure that bond distance, not only does the spectroscopy show us that we don't have all single bonds because we get a bond distance that's slightly smaller than a single bond, meaning that there's some double bond character to it, we actually see that all of the bond lengths are the same, which also is proof for resonance. So SO42- is a really great molecule because it demonstrates a lot of those principles, both resonance and expanded octet. So I have a bunch of different examples here of some expanded octet things. There are two interesting cases, beryllium and boron. These are what we call electron deficient structures. So I'll just sort of put a little note here, electron deficient. So these are also exceptions to the octet rule. And let me show you what I mean by that. So in the case of beryllium, if we bring our... I'll leave beryllium Cl2 as an example for you guys. This is a good one for you to do on your own. Let's just do boron F3. So boron has 3 electrons. Fluorine has 7. So 7 times 3 is 21. So this gives us a grand total of 24 electrons. So boron is definitely our least electronegative atom. So that's going to go in the middle. So our 24, we're going to take 24 minus 6 is going to give us 18. So we're going to draw our lone pairs in 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9. Now here's the interesting thing with BF3. Your tendency for BF3 would be to satisfy the octet by bringing a lone pair from the fluorine in. But we actually don't do that in this case. Boron is actually okay with 6 electrons. Let me show you why. So boron, for formal charge, boron brings 3 electrons to the party, minus 0 lone pairs, minus 1/2 of 6 electrons. This is going to give us a 0 formal charge. So boron is actually perfectly comfortable with just having 6 electrons. So the sort of the note that you want to make is that boron and beryllium are okay with 6 electrons. And the reason for that is because of formal charge. And what you're going to actually see is that beryllium is actually okay with only 4 electrons. So when you do beryllium, what you're going to see is that beryllium chloride is going to look like this. And beryllium is perfectly happy with just 4 electrons because, Again, when you do formal charge on the beryllium, this is going to give a 0 formal charge. So beryllium and boron are examples where you can have less than the 8 electrons around it. They're called electron deficient examples. So I just wanted to point that out because those are two other exceptions to the octet rule. That's not expanded octet. So let's look at one or two examples of expanded octet. We'll do something like SF6. This is a good example. So sulfur brings 6 electrons to the party. Fluorine brings 7. There's 6 of those. So 7 times 6 is, 7 times 6 is 42. So this is going to give us a grand total of 48 electrons. So when we draw this structure, we're going to draw S with 6 F's around it. Already we can see that in order to make this skeletal structure, we have to break the octet rule. The sulfur has 6 atoms around it, so it is automatically not going to be an octet molecule. There's no choice like we showed in SO42-. So we take 48 minus 2, 4, 6, 8, 10, 12. That's going to give us 36. Now we start putting our lone pairs in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 times 2 is 36. That's going to give us 0. So we have a good Lewis structure right here. And if you do formal charge, for this structure, you're going to have, for the sulfur, you're going to have 6 minus 0 minus 1/2 of 12 is going to equal 0. And for each fluorine, you're going to have 7 minus 6 minus 1/2 of 2 is going to give 0. So that is a good Lewis structure. Xenon F4. So this is one of those cases where the noble gases do actually, with something as strong as fluorine, fluorine can actually steal some electrons from a noble gas that's a little bit further down on the periodic table. So we have xenon brings 8 electrons to the party. Fluorine brings 7 electrons times 4. 7 times 4 is 28, so this is going to give us a total of 36. So we're going to put our 4 fluorines around the xenon. So 36 minus 2, 4, 6, 8. That's going to give us, 28 electrons left. So now let's start putting our lone pairs. So we're going to put 2, 4, 6. We're going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that maxes out our fluorines. So that's going to max out our fluorines at 24. So fluorines cannot expand their octet. They are locked into 2s2, 2p6. So they can only take 8. So we can't continue to put lone pairs onto the fluorines. So this is going to give us a total of 4 electrons left. So the only place that we can put electrons is on the xenon. So a xenon can expand its octet. It's below the 3rd row. So xenon can take those remaining 2 lone pairs. So this is going to give us minus 4 is 0. So let's do some formal charge calculations. So for xenon, we have 8 minus 4 for the lone pairs, minus 1/2 of 2, 4, 6, 8 is going to give us 0, so that's good. And for a representative fluorine, we're going to have 7 minus 6 minus 1/2 of 2 is also going to equal 0. So that is a good structure for xenon tetrafluoride. And our last structure is going to be ClO2 minus. So we'll put in this case, we'll do our Cl is going to bring 7 electrons to the party. Our O's are going to bring 6 times 2 is 12. And then we have a charge of -1. So this is going to be, a grand total of 20. So 7 plus 1 is 8, plus 12 is 20. And I denote in this case that the central atom is Cl. So we're going to put Cl with 2 oxygens around it. So we're going to subtract 4 from this. That's going to leave us with 16. So we're going to have 1, 2, 3, 4, 5, 6. So 2, 4, 6, 8, 10, 12. So we're going to do 16 minus 12 is going to leave us with 4. So that 4 is going to go, we cannot expand the octet of oxygen because those are in the second period. So that's going to leave us with 2 electrons, so minus 4 is going to give us 0. And in this case, let's do our formal charge. So we have our formal charge on the oxygen. So at this point, you can start to see that this oxygen is going to be 6 minus 1 is going to be a negative 1, a negative 1. You can do the formal charges. And the chlorine is going to be our 7 minus 1, 2, 3, 4, 5, 6. So this is going to be a positive 1. So I actually, in this case, we should look to see if we can get these formal charges down some. Can we make this a better structure? And we can. So in this case, we can make this a better structure by moving one of these lone pairs in as a double bond. So if we erase, in this case, one of these lone pairs and shift it in, what this is going to do for us now, if we recompute our formal charges, this oxygen is now going to have a 0 formal charge, 6 minus 4 minus 2. This chlorine now is going to be 7 minus 4 minus 3 is 0. And this is just going to be a minus 1. So this is going to be our proper Lewis structure for ClO2 minus. And again, here is another case where you can have resonance. So we can draw the other Lewis structure for this. So you're always looking for a case where you can have resonance. So here's another example of where you have expanded octet, and that expanded octet leads to a resonance structure. So this goes over the basics of drawing Lewis structures. This covers the vast majority of what we would expect. The only other example of something that we would have to draw would be a Lewis structure for a complete molecule. And we'll probably do this one in class the next time we have class, but I wanted to just introduce this. So in this case, drawing the Lewis structure is going to involve looking at each atom and making sure that its octet is satisfied. So we'll look at this next time, but the rules that we've covered basically demonstrate how you can do any example, whether it is a simple example where you don't have expanded octet, the central atom is in the second row, or where you have expanded octet where the central atom is in the third row or below. So just keep in mind to follow the steps. Make sure you're very pedantic about the steps. Make sure that you constantly are thinking about lowering formal charge, making double bonds to lower formal charge if you can. If you have a structure where you can have resonance, thinking about that so that you don't miss resonance. But these will all be things that will kind of come up on the exam, especially when you have expanded octet.